Hello everyone, this is Professor Keen. Suppose that you were walking along and you picked up a stone like this. It's a rough stone around the edges, about the size of a golf ball. It's got some shiny spots on it and it's black in color. Otherwise, it seems quite ordinary. Suppose then you picked up another stone. I got this one right outside of our science building here at Wisconsin Lutheran College. It looks similar, rough around the edges. It's got some red shiny flecks in it. About the same size, maybe a little bit smaller. Suppose you picked up another one. This one looks very similar to the second stone. Again, kind of a reddish hue with some shiny flecks in it, kind of black and red flecks. Here's another one I found. This is a white stone, a bit smaller than the others, but rough. And here's a little bit fancier stone. This is a semi-transparent stone with a nice rhomboid kind of structure. This is called Iceland crystal or Iceland spar, sometimes also called calcite. We're going to come across this later on in the semester in the context of studying optics. It played an important part in the study of polarization. That's because, as we'll find, when you shine a beam of light through this crystal, the beam of light will get broken into two different beams of light that have different polarizations. We'll come back to this later. While these rocks have certain features that look similar and different, color, size, shape, and so on, there's one important feature that I would like to point out about this black rock. If you were to take this black rock and you were to set it on a small float, like a little piece of wood in a still pond, you would find that over time this rock will twist and orient in such a way that a certain part of it is always going to face in the same direction. So if you take this rock, set it on the boat, and then you twist it again, eventually it will swing back around and face in the same direction. This is called a lodestone. It has this interesting property of orienting itself with respect to the Earth. This is perhaps more stunning when you take a powerful magnet like this and you set rocks on top of it. So if I were to take this rock, set this red rock on top of it, and slowly turn it, this red rock will fall off. Same with the other red rock. Same with this white rock. I set it on top of it and lean it, it will fall off. What about the calcite? Set it on top, slowly rotate it, it will fall off. Now, what about if I take this rock right here, this lodestone, and I turn it? You'll notice that it sticks. You've probably seen things like this quite often. You're all very familiar with magnetism, I suppose, from seeing magnets stick to your refrigerator. But this raises a very interesting question. What is it fundamentally that's different about this rock than the other rocks? After all, there's different colors, but this is a very strange thing. One thing can pull on another thing across empty space, like that. What is it that causes this? People have studied magnetism for many, many years. There's been a lot of scientific texts written on this, but I would like you to place yourself in a position, kind of forget what you've learned about magnetic fields and electrons and things like that. After all, those are modern concepts, and people have been studying magnetism far before the 1800s when those concepts were initiated. So I want you to kind of be naive for a moment and ask yourself, what is it that causes a lodestone to act in this peculiar way? Today we're going to begin our study of magnetism. We have to start somewhere, so we're going to start with one of the most famous books about magnetism, though definitely not the first. This book is called On the Magnet by William Gilbert. He wrote it in Latin. It was called De Magnete. William Gilbert was a physician, a doctor who worked in the service of Queen Elizabeth around 1600. And he begins his treatise on the magnet by explaining some of the kind of experimental observations that one can make of these lodestones, or naturally occurring magnetic rocks. One of the first things he does is he talks about how if you take this lodestone and you put it on a float, it will always turn around so that one edge of that rock is oriented toward Earth's North Pole. Gilbert calls the end of the magnet, or the end of the lodestone that points toward Earth's North Pole, he calls that the South Pole of the magnet. In fact, he goes on to mock those who call that end of the lodestone the North Pole of the lodestone. Interestingly, as we'll find, his conventions are exactly the opposite of the way we talk about it today. But that's not a critical point right now. It's just something you might want to think about as we continue our studies. Another thing that he mentions is that if you take a small piece of iron and you rub it against a lodestone, and then you take this piece of iron and balance it, it too will twist so as to orient along a north-south direction, along what's called a magnetic meridian, or a meridian. He says that it acts like a versorium. A versorium, that's a term we don't use so much anymore. He also calls it a mariner's compass, or as we would call it today, simply a compass. And he mentions that these compasses are very useful for people finding their direction when they're at sea. The compass, however, does not always, and this is a third point that he mentions, it does not always lie exactly in the north-south direction when it's magnetized. Rather, sometimes a compass needle will somewhat deviate to the east or to the west of this magnetic meridian. He's going to talk more about that in the course of his book. We're going to ignore some of those chapters. On the Magnet is quite a long book, and we're going to focus on a few of the what I think are the most important chapters. But in any case, in this chapter, he says we're going to ignore these slight deviations that the compass needle makes from the north-south directions. Okay, so what does he do? So in this chapter that we're going to be looking at, one of the things that Gilbert does is he tries to provide some context for his magnetic discoveries. And one of the ways he does that is by describing some of the earlier thinkers, how they thought about magnetism. He calls these the early elementarian thinkers, and I'll come back to that term in a few minutes. But some of them are, he lists, I think, 5 or 6 of them, and he presents their worldview, their view of how magnets work, to contrast them to the presentation that he is going to make of why magnets work. One of the people he talks about is Martinus Cortesius. And what Martinus Cortesius thinks is that if you rub a piece of iron, it is going to be oriented, sure, that's fine, but he says the attractive point, the point toward which it's oriented, lies outside of the Earth, somewhere in the heavens, in fact, somewhere beyond the heavens. So there is an attraction, but the source of the attraction is not the Earth itself, it's somewhere beyond the heavens, beyond the sky. He also mentions Petrus Peregrinus, who believes that when you hold up an iron, a magnetized piece of iron, it points certainly in the north-south direction, but that's because it is pointing toward Polaris, or the North Star. In other words, the attraction of it lies, again, outside of the Earth. He also mentions Cardan, who says that the iron compass needle is pointed toward Ursa Major. That is, you might know, the Big Bear, and you probably know it better by the hindquarters of the Big Bear constellation, which we call the Big Dipper. That's an asterism, or a group of stars. He also mentions a Frenchman named Bessard, who also believes that compass needles are oriented toward a point in the heavens, a set of stars. He says it points toward the pole of the zodiac. So what are some of the common features of all these? Notice that all of these thinkers that preceded Gilbert thought that the power or the potency that was able to attract a magnetic object like an iron compass needle lies outside of the Earth. Gilbert, on the other hand, says that he seeks the power or the potency that acts on the magnet here on Earth. So he says that these people tend to have a tendency to look to exotic places, the heavens, the skies, for the source of action when you can find it right here on Earth. Okay? What I'm going to do now is I'm going to break away from my webcam and offer some comments on the ancient or traditional or medieval worldview in which Gilbert was working. I think this will give us a better understanding of what he's trying to do. So I'm going to cut away from my webcam, and I'm going to make a few comments on the worldview in which, so these are background comments, on the ancient, we might say it's the ancient or the medieval, I would say the traditional worldview in which, within which Gilbert was working. I think really to understand the language and the kinds of things he's talking about, it's very helpful to think about the ideas that were circulating at his time. So let's spend a few minutes talking about that. First of all, the first point I'd like to make is we are seeing at this time a transition from a geocentric to a heliocentric worldview. Transition from geocentric to a heliocentric predominant worldview. Okay. Those of you who have taken my Physics 101 astronomy class will have a very good understanding of this, but I think most of you understand the difference between geocentrism and heliocentrism. So the geocentric worldview believes that the Earth, geo, is at the center of the universe. They would say the center of the world meaning universe. And just before the time of Gilbert, remember Gilbert wrote this right around 1600, just before the time of Gilbert, the work of Copernicus. Copernicus wrote a book called On the Revolutions of the Heavenly Spheres, published in 1543. And in this one, he defended a heliocentric worldview where the sun was placed at the center of the universe, at the center, definitely the center of our solar system, but also at the center of the universe, or the center of the world, as he described it. Okay, so this geocentric worldview was the ancient and medieval and traditional worldview. The heliocentric worldview is now becoming seriously considered. So let's take a moment to think about this geocentric worldview. So I'm going to draw a picture right here. According to the geocentric worldview, we have the Earth, and I'm going to draw a couple of poles. That's the north and south pole of the Earth, and this is the equator of the Earth. And according to this geocentric worldview, this is going to be a bit of a simplification, but I think you'll get the point. The idea is the Earth is surrounded by a huge sphere called the celestial sphere. And this celestial sphere also has an equator, draw it like this, and it has poles that lie directly above and below the Earth's poles. And the idea is that the Earth sits still, and this celestial sphere rotates around the Earth. So it rotates around the Earth like this. The way I'm simplifying this is there's actually a whole series of spheres that carry the different planets and the sun and the moon and so on, but I want to focus on the celestial sphere that holds the stars. So this celestial sphere has various stars on it. So on the north, on the top pole right here, you have Polaris. That is the North Star. So if you're standing on the North Pole of the Earth and you look straight up, you would see Polaris. If you're standing on the equator and you look straight up, you'd be looking in this direction, so you'd have to look at the horizon to see Polaris. Anyhow, there are many, many stars that lie on this celestial sphere according to this worldview. I'm going to draw a whole bunch of stars. You can think of these stars as all pasted or glued or stuck to this huge celestial sphere. And as this celestial sphere rotates around every day, someone who's standing on the Earth will see them rise and set. Okay. This, by the way, I'll mention this right here. This is called the celestial equator. Just like the Earth has an equator, there's a celestial equator. It's the center belt of the celestial sphere that rotates around. And there's also, so I mentioned there are a whole bunch of stars that are stuck to this celestial sphere. There are a certain set of constellations. I'm going to draw a band like this at a kind of a funny angle. Okay, if you think of a belt like this, okay, there's a certain belt that if you think about it being broken up like this into 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 sections to this belt. And on this belt, there lie certain sets of stars or constellations that we call the zodiac. Here we have Aries. I'm drawing the symbols for them. Okay, so you might think about there's a certain set of stars in this region, and those stars form a constellation that's right in this belt of the celestial sphere called Aries. Then we have Taurus right here. That's the bull. And then we have Gemini right here. That's the twins. And then we have, I'm using the traditional symbols for these. You might not know them. Cancer, the crab. Okay. And after that, oh, let me see. We have Cancer. And then we have Leo, the lion. Okay. That's Leo. And then we have Virgo. Kind of looks like an M with a little extra loop right there. That's Virgo, the virgin. Next we have Libra, the scale. And next we have Scorpio, the scorpion. And then we have Sagittarius, the archer, right here. And next we have Capricorn. And then we have Aquarius. And then we have Pisces. You don't have to remember all these. If you were in my astronomy course, you would remember all these. But those are a set of constellations that form the zodiac. There are 12 special constellations. There are, of course, constellations all over the celestial sphere, but those are special constellations. They're special because the sun passes in front of them, each of these, over the course of the year. Okay? And let me draw something else while I'm drawing this. So if you were to draw lines that connect the north and the south pole of the Earth, these would be called the meridians. Okay, so all these little lines in here, I know this is a little bit tight, but these are the meridians. Okay, they go from the north to the south pole of the Earth. And why am I drawing this? Because you'll remember that the previous thinkers, when they were thinking about magnetism, they believed that when you hold a magnet, it is pointed in a certain direction because it's either pointed toward Polaris, the North Star, or perhaps because it's pointed toward the pole of the zodiac, some star right up here. It's pointed toward that point, or even perhaps some point beyond the celestial sphere. And what Gilbert says is no, in fact, the action of a magnet is governed by the Earth itself. Okay, so that's one thing I'd like to mention about the geocentric worldview. The second point I'd like to make is that the work of Gilbert would influence Johannes Kepler. So Gilbert had an important influence on Johannes Kepler. You might recall that Kepler came up with some laws of planetary motion slightly after Gilbert, and Kepler also, like Copernicus, was a heliocentrist. He believed that the planets go around the sun. Kepler argued, based on Gilbert's on the magnet, that the motion of the planets around the sun was governed by some invisible force not unlike Gilbert's magnetism. In fact, Kepler, in his book Epitome of Copernican Astronomy, specifically references the work of Gilbert and says that Gilbert might be onto something in trying to understand the motion of the planets. Of course, later on, Newton will say that the correct force to be thinking about is gravitation, not magnetism. Okay? Another point that I'd like to make is that Gilbert, and this is going to be an important point, Gilbert speaks of powers and potencies. Of powers and potencies, potentials, potencies that things possess within themselves. So, within themselves, that allow them to act. This allows them to act on other things. Okay, so notice that I'll explain this more in the coming minutes. But what he says here is that whereas previous medieval thinkers said the powers or potencies, the abilities to affect a magnet, lay outside of the Earth, what Gilbert is going to argue is these powers or potencies lie within the magnet and within the Earth himself. So he just kind of locates the power to act within the lodestone and within the Earth rather than outside of the Earth and in the heavens. This talk of powers and potencies eventually in the modern era would give way to the idea of inert matter or atoms that are governed by laws from outside of themselves. So Gilbert is still working to some extent within this traditional view that things have powers or potencies within themselves. Okay? In other words, people, animals, plants, rocks, atoms were in the ancient and traditional worldview seen to possess certain powers or potentials to act on other things. What we would now call laws of physics would in this older view really be a summary of these powers that thing had by virtue of being what they are. So a human being has certain powers by virtue of being a human being. A tree has certain powers by virtue of being a tree. A rock has certain powers by virtue of being a rock. In the modern view, the laws of physics, whether Kepler's laws of planetary motion or the law of conservation of energy that comes about in the 1800s, these are laws imposed on nature from the outside. And nature by itself would simply be comprised of powerless, inert, kind of inactive bits of aimless matter. And this is really a major difference between the traditional view and modernism. It's interesting that William Gilbert does adopt this traditional worldview of things themselves having powers or potencies, but he also mentions on page 4 what the source of these powers and potencies is. He believes that these powers and potencies come from God himself. Powers and potencies in natural objects have God as their source. He calls God the supreme artificer. This is on page 4. So just like, today if you were to build a Ferrari, you would say that Ferrari has the power to go fast. But of course that Ferrari was built by an engineer. So the engineer gave it the power to do so. But once that engineer has built the Ferrari, then that Ferrari does itself have the power or the potency to go fast. Now also, as I mentioned before, Gilbert uses the Earth, not the heavens. The Earth, not the heavens or the things above the Earth. Not the heavens. Don't think about heavens like the place you go when you die, but the heavens is everything above the Earth. Gilbert uses the Earth, not the heavens, as the starting point. It's a starting point in understanding magnetism. He has a very earthy approach to this, a mundane approach. And he goes on to mention that just as the Earth has a natural orientation with respect to the skies or the heavens, so too a lodestone has a natural orientation with respect to the Earth. So just as the Earth has a particular orientation with respect to the heavens, right? After all, the pole of the Earth lines up with the North Star, the Polaris. He says, so too does the lodestone or other magnetized objects. Does the lodestone have a natural orientation with respect to the Earth itself? Okay. Now, this raises the question immediately. Here's the question. Why is the Earth oriented in the way it is? This is a question that he asks. In particular, why is it oriented straight toward Polaris? That's not obvious that it should be oriented that way. And he mentions that the pole of the Earth is at a 23 degree, between 23 and 24 degree angle with respect to the axis of this zodiac. So if you think about the zodiac, he calls it the ecliptic also. The axis of that has a 23 degree and 29 second angle with respect to it. So he attributes that to some kinds of magnetic forces. Okay. Why don't we stop there, and we will pick up our discussion of Gilbert and his On the Magnet next time.